In this video, we're going to talk about linear independence in the context of vector spaces, and we'll define what it means for a set of vectors to be a basis. Okay, so let's begin with the definition of linear independence. And this is going to look really similar to the definition that we saw before, just with a minor difference. So we say that an index set of vectors, v1 up until vp, in a vector space V, and that's what's different. Before, when we talked about linear independence, our vectors were in Rn, but now they're in some general vector space V. So that our set of vectors is linearly independent if the equation c1 times v1 plus dot 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 plus cp times vp equals 0, so this homogeneous equation, has only the trivial solution. So the trivial solution, remember, is, let's put this in a different color actually. The trivial solution, remember, is when c1 all the way until cp, all of those weights, all of those coefficients equal 0. So that's the only solution to this equation. Then we say our set of vectors is linearly independent. But if there is a solution where not all of the ci's equal 0, then we say that our set of vectors is linearly dependent. So again, really similar to the definition that we saw before. The only difference is now we're talking about our vectors being in some vector space V. Before, when we introduced independence and dependence, our vectors were in Rn explicitly. Okay, so let's do an example. So let's do an example where we show that we can generalize this and talk not just about vectors, but about polynomials. So is the set that contains P1, P2, and P3, three polynomials, linearly independent? So that's Li. Or linearly dependent, that's LD. So our polynomials here are, the first one's 3t, the second polynomial, P2, is t plus 1, and the third polynomial is 5t minus 1. Okay, so there's something I want to notice about these. So these polynomials. So if I look at my third polynomial, 5t minus 1, I can write that as something times the first polynomial, something times 3t, plus something times the second polynomial, which was t plus 1. In other words, I can write 5t minus 1 as a linear combination of p1 of t and p2 of t. And if we think about it a little bit, and I'd encourage you guys to pause the video for about 30 seconds or so, and see if you can think about, well, what are the numbers that go in here? And they have to be real numbers. They can't be anything with a variable to make this equal 5t minus 1. Okay, so hopefully you guys did that. Hopefully you guys paused the video for about 30 seconds to think about this. Turns out if I plug in 2 here and negative 1 into the second parentheses, it's going to end up equaling 5t minus 1. So because I can write one of my polynomials as a linear combination of the others, like we've seen before, that means our set is linearly dependent. Our set is linearly dependent. So what we just noticed is P3 equaled to P1 minus P2. I can write one of my polynomials as a linear combination of the others. In the context of this definition, if we just rewrote this, we would get that 0 equaled to P1 minus P2 minus P3. So notice that there is a linear combination that equals 0, where not all of the weights are 0. Like one of the weights is 2, another one of the weights is negative 1, and then there's another weight that's also negative 1. So my polynomials in part A are linearly dependent. Okay, let's do another part of this example. What about these new polynomials? What if the first polynomial is 1, the second polynomial is t, and the third polynomial is t squared? So these polynomials, it turns out, are linearly independent. They are linearly independent. So I want to give you 2 reasons why. So the first reason is going to be more of a technical reason. The second reason I think is a little bit more conceptual. So the first reason is, if we think about the definition of linear independence and dependence, if I look at an equation like c1 times my first polynomial, first element, plus c2 times my second element, second polynomial, t, plus c3 times the third thing, t squared, and I set that equal to 0. So I want to know what values of C1, C2, and C3 are going to make the two sides of this equation equal. And they need to be equal for all values of t, no matter what I plug in for t. So this must be true. We want this to be true for all t. That's really important. So this is a polynomial equation. It's got to be true for all values of t. That's what I want. Okay, so what I'm going to do, just so I don't have to continue to write this whole thing on the left-hand side, I'm just going to call this f of t. This is some polynomial. Okay, so I need this f of t to be equal to 0 for all values of t. So for that to happen, there's one thing that I want to notice. There's sort of a problem that I run into, which is that the fact that f of t, my polynomial on the left-hand side, has degree at most 2. It has degree at most 2. It might not necessarily be equal to 2 because what if this coefficient is 0? If that coefficient C3 was 0, then the degree would be less than 2. Okay, so since this polynomial has degree at most 2, which means that the equation f of t equals 0 has at most 2 solutions. At most 2 solutions. In other words, there's at most 2 values of t that I can plug in that are going to make f of t actually equal 0. Okay. There is one caveat though to that, which is unless all of my coefficients equal 0, unless C1 and C2 and C3 all equal 0. To visualize why a little bit, let's think about 2 possibilities. Well, what if C3, the coefficient of t squared, was not 0? Well, if that was not 0, and if I looked at the graph of f of t, well, if C3 was not 0, I'd have a quadratic. And the graph of a quadratic can cross the x-axis at most twice. So if I had something like this, it can cross the x-axis at most twice if it's a quadratic. But I need this to be true for all t. I need my function to be equal to 0 for all t. So I need my function to just always be on the x-axis. I need it to be the 0 polynomial in essence. Okay, on the flip side, well, what if C3 equals 0? What if it wasn't a quadratic? If C3 equals 0, then I have a line. And a line, typically, is going to cross the x-axis once. But I need it to cross the x-axis for every single value of t. And the only thing that's going to get it done is if I make all the coefficients 0. So C1, C2, and C3, all of them have to be 0. Okay, so I promised I'd give you guys one other reason for why these 3 polynomials are linearly independent. And this one I think is a little bit more conceptual. It's a little bit quicker, I think, as well. Okay, so the other reason is that none of these 3 polynomials, P1, P2, and P3, are linear combinations of the others. Okay, so what do I mean by that? So for example, if I look at the third polynomial, t squared, can I write that as something times t plus something times 1? And remember, for me to form a legal linear combination, these coefficients here, they need to be scalars. So I can't pick variables here. Like I can't pick a t here and a 0 here and be like, oh yeah, that's going to be t squared. That's not allowed because I have to pick real numbers. I can't pick a variable. I can't pick a function like t. So if I think about it a little bit, there are no scalars that work. There are no scalars, no real numbers that work, that I can plug into these 2 blanks to give me t squared. The right-hand side is never going to have a degree of 2. The biggest the degree of the right-hand side could be is 1. Okay, so next I want to define a basis. Okay, so here is the definition. So if H is a subspace of some vector space V, so this symbol that is, it looks like a B. This is technically a script, what's called a script B. A script B. What makes it a script B is the fact that it sort of has this, tail sort of flourishing at the end, at one of the corners. So script B, that's just my notation that I'll use to refer to the basis. So this has the vectors B1 up to BP in it. So these are vectors in V. So we say that this set is a basis for H, for the subspace, if it has two properties. So the set needs to be linearly independent, and the set needs to span whatever subspace we're talking about. In this case, I'm talking about H. So we've actually seen examples in Rn of sets that are a basis for Rn. The most common one is here in example 2. So the set of vectors E1, E2, all the way up until En, they're what's called the standard basis for Rn. It's sort of like the simplest basis that we have for Rn. So, and it's the most commonly used, which is why it's called the standard basis. So remember, E1 is the first column of the identity matrix. It's 1, 0, and then just a bunch of zeros under the 1. E2 is 0, 1, so the 1 is in the second entry, and then a bunch of zeros underneath that. So that's what E2 is. So there are many other bases. So basis is the singular version. Bases is plural. So bases is plural. That's why I say more than one basis. There are many bases for Rn. This is just one example. Okay, so let's do another example. So we can talk about bases for things that are not Rn. For example, Pn, the set of polynomials of degree at most n. For example, with Pn, the polynomials 1, t, t squared, all the way up until Tn, they form a basis for it, and they're called the standard basis. Okay, so the reason why these vectors are a basis for Pn is because, so I need two things. They got to be linearly independent, and they have to span my set. They got to span Pn. So they're linearly independent for the same reason that in our previous example, the polynomials 1, t, and t squared, that set is linearly independent. The reason is really, really similar to that. And these vectors clearly span Pn. And the reason for that is things in Pn look like, so if P of t is something in Pn, it looks like a naught plus a1t plus dot 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 up until an t to the n. So I noticed that a naught, for example, is a naught times 1. And then the next term is a1 times t. All the way up until the last term is an times t to the n. So I have a linear combination of 1 t, t squared, all the way up until tn. And that's what it means for these functions, these polynomials, to span Pn. I can write any element of Pn as a linear combination of 1, t, all the way up until Tn. So clearly, the set spans Pn. Okay, so I want to state a key fact about bases that we'll see again in section 4.5. So this is a little bit of a preview. So any basis of my subspace, H, will have the same number of vectors. So we'll see this in section 4.5. Okay, and the number of vectors that are in a basis has a special name. It's called the dimension of the subspace, or the dimension of the vector space. And again, we'll see this more in detail in section 4.5. But I want to introduce this to you guys now because it's pretty easy to state what the dimension of each of these subspaces is. So if I count the number of vectors in this basis right here, I can state what the dimension is. The dimension And this example is n, because there are n vectors in this basis. In fact, any basis for Rn should have n vectors. That's what this fact here says. So in example 3, the dimension is what? How many elements are there in this standard basis? 1, t squared up until t to the n. Well, there are n plus 1. Remember, it doesn't start at t to the 1, it starts at 1, which is technically at t to the 0 in a sense. So there are n plus 1 elements in this basis. That's why the dimension is n plus 1. Okay, so let's state a key theorem now. Okay, so this is just summing up what we sort of noticed. So a set of vectors v1 up until vn is a basis for Rn, this we've sort of seen before, if and only if. What does it take for a bunch of vectors to be a basis for Rn? Well, when I form the matrix that has those vectors as columns, so v1 up until vn as columns, to be a basis, they have to be linearly independent, and they have to span Rn. And to do those two things, I need pivots in each column and row. So my matrix needs to have a pivot in each column and row. And we know that's equivalent to saying that my matrix A is invertible. So let's box this. So in Rn, a set of vectors is a basis for it, is a basis for Rn, if and only if my matrix that I get when I put those vectors as the columns is invertible. Okay, so let's do an example. So is the set of vectors, so these three vectors, is this a basis of R3? So the way I check it according to this result that I've just stated up here is, so we put these vectors as columns in a matrix. So in the first column, the second column, 0, 1, negative 3, the third column. I put them as columns in a matrix, and then I row reduce it to check to see if there's a pivot in each column and row. Okay, so what would I do? I would do 4 times the first row and add that to the third row, and substitute into the third row. So doing this, the first row and the second row stay the same. 1, negative 2, 0, 0, 1, 1. But the third row changes. I'll get 0, and then I'll get negative 8 plus 5, which is negative 3. And then 0 added to negative 3 is still negative 3. And now there's just one more row operation that I need to do. So I just would do 3 times the second row and add that to the third row, and substitute into the third row. Let's see, do I have enough room to write that here? I might. Okay, yes, I think I do. So the first 2 rows do the same. 1, negative 2, 0, 0, 1, 1. But the third row now changes. The third row actually becomes all zeros. Okay, so now we know what the pivots are. It's this one in the first row, and this one in the next row. So because not all the columns have pivots, and not all the rows, not all the columns slash rows, not all the rows slash columns have pivots, that means that our vectors here are not a basis. So the vectors are not a basis for R3. Okay, so I want to end with one more quick example. So let's find a basis for the set of vectors in R2 that are on the line y equals 4x. Okay, so let's draw a picture to help us visualize what's going on here. Okay, so let's draw our axes, our x, y axes, and then I'm going to draw this line, y equals 4x on it. So y equals 4x, it goes through the origin, and it has a slope of 4. So I know, for example, when x is 1, the y value is 4. When x is 2, the y value is 8 on this line. Okay, so what I want to do is I want to describe the set of vectors that are on this line and give a basis for that set of vectors. Okay, so I notice that, if I just take one sort of arbitrary vector on this line, For example, if I take this vector right here, all the other vectors on this line are multiples of this vector that I've just drawn in, this red vector. So we're looking at all multiples of that red vector that I just drew in. So that red vector went 1 in the x direction and 4 in the y direction. Okay. So in other words, our set right here is the span of this vector. It's the span of the vector 1, 4. So this vector right here is going to form our basis. So our basis, so let me practice writing this script B, is going to be the set. So set notation that just has the vector 1, 4 in it. Because I'm only taking linear combinations of this vector to get all the other vectors on this line. When I take a linear combination of just one vector, I'm just forming the multiples of that vector. So this is my basis.